Hello, everyone. I hope everybody's fine and healthy and happy and everything is fine. We want to start talking about rate of change in this unit. A rate of change of a function with respect to the independent variable x may be an average rate of change, or it may be an instantaneous rate of change. So an average rate of change is a rate of change of a function over an interval. So there must be an interval or two endpoints involved when we are asked to calculate the average rate of change. However, in case of instantaneous rate of change, that is the rate of change of a function at a specific point. And this specific point is just one single point. So if you have one point on the graph of a function and you want to find the rate of change, that is called instantaneous rate of change, which means the rate of change at that single point. But whenever you have an interval and you have 2 points on the graph of a function and you want to find the rate of change, then that rate of change is called average rate of change. Okay, so geometrically speaking, average rate of change corresponds to the slope of the secant line connecting the two endpoints of the interval. Secant line is a line that intersects a graph at two or more points, whereas in case of instantaneous rate of change, it corresponds to the slope of the tangent line passing through that single point, which is also called point of tangency on the graph of a function. So the tangent line is of course a line that intersects a graph at one single point. And that point is called point of tangency. But a secant line intersects the graph at more than one point. So this is just a schematic diagram. It shows the graph of function y equals f of x. And we have 2 points on the graph of this function, point P and point Q. The coordinates are x1, y1 for point P and x2, y2 for point Q. When we join these 2 points, points P and Q, then we are generating a secant line. And this secant line, of course, it has a slope, and the slope is always found by finding rise over run. So the rise here would be the amount of change in y. So this would be delta y, or change in y, and this distance here would be delta x, or change in x. And we know that the slope of any line is rise over run. So we can write average rate of change, AROC, equals delta y over delta x, which means y2 minus y1, that is the amount of change in y, divided by x2 minus x1, that is the change in the amount of x. Change in the dependent variable divided by the change in the independent variable. And in using function notation, instead of y2 minus y1, you can say f at x2 minus f at x1. It's just the same as y2, y1, except that we are using function notation. Geometrically speaking, we said that it represents the slope of the secant line. So the average rate of change is the slope of the secant line. Now, if you want to find the rate of change at one single point, that is point P, known as point of tangency, then you're not talking about the secant line PQ. You are talking about the tangent line, which touches the graph at one single point, point P. And instantaneous rate of change represents that slope of tangent, m sub t. In order to calculate the slope of tangent line, we are using limits, which we are going to study later on in the course. But for now, if you want to calculate average rate of change, well, it's like very easy. You just have to calculate this quotient, and that is it. But in case of calculating instantaneous rate of change, I should say estimating instantaneous rate of change, what we do, we are selecting 2 points that are very, very, very close to one another. Okay? Then in that case, we are actually finding the slope of that secant line for those 2 points that are extremely, extremely close to one another, and we claim that our answer is a good estimation of the slope of tangent. So that's the trick here. But if you want to exactly calculate the slope of tangent, it can be done later on using the idea of limits. But because we have not learned about limits yet, that's why we don't talk about it now, and we only mention about estimating the slope of tangent or estimating the instantaneous rate of change. So these are the two rates of change we have. As I said, average rate of change for 2 points, instantaneous rate of change for one single point. Now here it says, given this quadratic function f of x equals 4 minus x squared, find the average rate of change between x equals -2 and x equals 3. And also, it says find the instantaneous rate of change at x equals 1. So you see that here, 2 points are involved for finding the average rate of change, and over there, there's only 1 point involved in order to find the instantaneous rate of change. So what we're going to say average rate of change equals what we said before. It's going to be f at x2 minus f at x1 over x2 minus x1, which is actually the same rise over run. So here, numerically, it's f at 3 minus f at -2 divided by 3 minus -2. The denominator is 5, obviously. The numerator is going to be 4 minus 3 squared. I'm substituting 3 for x, minus, and then 4 minus -2 squared. So if you do the math, this is 4 minus 3 squared. That is 4 minus 9, which would be -5. So that's -5. And then 4 minus 4 is just 0, so minus 0 all over 5. The answer is -1. So we see that the average rate of change of this function between x equals -2 and x equals 3 is equal to -1. Geometrically speaking, it is the slope of the secant line that is drawn from the first point to the second point. Now, it says also find the instantaneous rate of change at x equals 1. So for this one, instantaneous rate of change, as I said, we can only find an estimation. So we're going to select the 2 points, one at x equals 1. The other one, the second point, will be very, very close to this point. So I'm going to go by f at 1.01 minus f at 1 divided by 1.01 minus 1. So I'm selecting arbitrarily a point that is very close to x equals 1. And the point I selected is 1.01. So here we end up with 4 minus 1.01 squared, and then minus 4 minus 1 squared, which is, of course, 3, all over 0.01. So now all we need is a calculator. 4 minus 3 is just 1. So we end up with 1 minus 1.01 squared divided by 0.01. And we need a calculator to calculate this. So 1 minus 1.01 all squared. That's the numerator. And we're going to divide it by the 0.01 in the denominator. The answer is -2.01. So -2.01. So this is roughly, approximately equal to -2. So the instantaneous rate of change at x equals 1 is approximately -2, because we got -2.01, which is very close to -2. And the average rate of change between the 2 points, x equals -2 and x equals 3, is actually equal to -1. So we did find a very good approximation, a very good estimation of the instantaneous rate of change at x equals 1. The answer was -2. And we also found an exact calculation of the average rate of change between x equals -2 and 3, and the answer was -1. Now, sometimes instead of the equation, they give you a table of values. For example, this could be like a balloon that is being filled with air, and at different time values, like 3 seconds, 6 seconds, 9 seconds, 12 seconds, the volume of this balloon in cubic centimeters is given here. So after 3 seconds, no, first of all, at 0 seconds initially, the volume of the air inside the balloon is 0, because we have not started filling in the balloon with air yet. But then after 3 seconds, when a little bit of air is filled inside the balloon, the volume is 4.5 cubic centimeters. After 6 seconds, that volume increases to 35.5 cubic centimeters. After 9 seconds, 115.5, and so on and so forth. These are the values given in the table of values. And the question says find the average rate of change between t equals 3 seconds and t equals 9 seconds. So this time you see that no equation like y equals 4 minus x squared is given, but instead a table of values is given. So that's fine. We can still calculate the average rate of change. So we're going to say AROC, okay, equals change in volume in this case, change in volume divided by change in time. So what plays the role of y, the dependent variable, is the volume of the air inside the balloon. And what plays the role of the independent variable x, in this case, is time, which is measured in seconds. So delta V over delta T, or you can say V2 minus V1, or V sub 2 minus V sub 1 divided by T sub 2 minus T sub 1. And this is actually volume at T2 minus volume at T1. I'm using function notation on purpose here. So that would be volume after 9 seconds minus volume after 3 seconds divided by 9 minus 3. The denominator is 6. The numerator is going to be 115.5 minus 4.5 clearly. And I think if you subtract, it's going to be 111 divided by 6. So using the calculator, the calculator was dropped. So 111 divided by 6, it gives you 18.5 exactly. So 18.5. The numerator is volume measured in cubic centimeters, and the denominator is time measured in seconds. Therefore, the unit of measurement is going to be cubic centimeters per second. So the average rate of change of volume of the air inside this balloon with respect to time is 18.5 cubic centimeters per second between t equals 3 seconds and t equals 9 seconds. Okay, so to find the average rate of change, we may use table of values, or we may use the formula. It doesn't matter. And in order to calculate, or I should say estimate, the instantaneous rate of change, the trick we are using is that we are selecting the second point very, very close to the single point where we want to find the slope of tangent, such as I did earlier. I selected 1.01, which was a point very close to x equals 1. I could have selected 1.0001, for example. And then we calculate the average rate of change, and we claim that this rate of change is actually a very good estimation of the instantaneous rate of change at that required point. I hope you understood this discussion on average rate of change and instantaneous rate of change, and we will talk about this more in future. Thank you for your attention.